I'd like to introduce Chen. We're going to be talking about reversing and exploiting an Apple firmware update.
Okay, so is everybody able to hear me back there? Okay. Okay, so I'm going to be talking about reversing and exploiting an Apple firmware update. All right, so what I'll do is I'll periodically have like these summaries of the various sections of my talk. So the first section, motivating things and so forth. Okay, so this is the scenario, and I want to emphasize that this is like all post-exploitation. So what's happened is we've taken over somebody's Macintosh. However you do it, say you read Dino Diazovi and Charlie Miller's book, The Mac Hacker's Handbook, which is a great book, by the way. You found some zero-day, or or you social engineer somebody, whatever, and so you've taken over their box and you want to maintain control of it. Like no matter what, you need to have access to this machine. So that's our objective. So okay, that machine might be like just incredibly important, whatever or it might be just some fanboy that really gets on your nerves, whatever. Okay, so last year at Black Hat there was a proof of concept rootkit by this guy Jesse Daguano, and the thing with his rootkit is that if you reinstall the operating system, say you like wipe the hard drive, reinstall it, it's gone. If say you take the hard drive out, put a new one in, reinstall it, it's gone. And the thing is, we want to maintain control even if the user does that. That's our goal. So suppose that we found some zero-day, we use it, we took over somebody's box, and then Apple, somebody else discovers the same vulnerability, or Apple discovers it themselves, and then they patch that vulnerability. So in that case, the owner hears about this bug and says, oh, maybe I got owned. It might have been like, say, that recent Java vulnerability. So then the owner is paranoid and reinstalls the operating system from the media that comes with the machine. And then they safely update the patch level. When I say safely updating the patch level, I mean like it's not like the case that you say you own one of their boxes and then you can use that to corrupt the updating process. They safely update the patch level. Okay, so, and this is what I do all the time actually on my Mac. I'm constantly reinstalling the operating system because I am paranoid. Okay, so with these goals in mind, like there are some things that work in our favor. And one of the big things that works in our favor is that Apple has this habit of shipping products that just aren't ready. I don't know if people agree with me on this, like the product hasn't been fully tested and they just go ahead and ship it out. And then they say, oh, well, even though it has bugs and stuff, we'll just use like the early adopters as beta testers. And then they say, oh, well, we're going to later issue a firmware update to correct our bugs. So that's what they do. I mean, I don't think I'm crazy about it. I think this is just this is the way they do business. Is they just like, say, oh, well, we're not quite, done testing this thing, but let's just go ahead and ship it anyway. Then we'll issue a firmware update. So if you go to support.apple.com and then you do a search for, in the search box, you do a search for firmware update. A couple months ago when I did that search, there was almost 1,000 firmware updates available. And 1,000, that's a lot in my opinion. And another point is that the Mac world is very monocultural. And say like if you take over some Windows box, like a priori, you don't know what that box is. It could be an Asus, an Acer, a Dell, like a Lenovo, Toshiba, whatever. You don't know what it is. Generally, if you like say port scan some box and it's a Mac OS X machine, like 99.9% of the time it's going to be Apple hardware. So this is something that works in our favor, because if Apple had licensed Mac OS X to like multiple companies and stuff, then like the underlying hardware that they would choose would be probably be different from Apple in general. Okay, so all right, so let me just show you a picture. This is if you do a search on support.apple.com for firmware update, there's what is that number? 990. I can't even read that. 993. So if you go through that list, scroll through that list, then you see that Apple has firmware updates for a lot of stuff. So you can see they have firmware updates for graphics cards. Apple has used both ATI and NVIDIA. They have firmware updates for keyboards, the trackpad, the Bluetooth adapters, EFI, and Super Drive is their DVD drive things. Then their airport wireless products, even like that time capsule, those things that have I think either 500 gigs or 1 terabyte of storage. Even those things have had firmware updates. So there's firmware updates for all kinds of products. So it seems like across the whole product line, they have a habit of issuing firmware updates. So, but what we're going to do is we're going to concentrate on keyboards. That's what we're interested in. All right, so what can we do when we have control of the keyboard? So if you can't see that picture, well, that's a picture of a dog using some computer. So what can we do with control of the keyboard? So if you have control of the keyboard, you can pretty much do whatever the user is doing. Pretty much you can be just like the user sitting in front of the computer. So, all right. So one of the things that would be very handy is you can just shovel a shell right back to yourself if you have control of the keyboard. So how do we do that in Mac OS X? So by default in Mac OS X, there's this functionality called Spotlight, which allows you to search, kind of in some sense do a search of your whole system. And so you invoke that by typing command space. And then in the upper right-hand corner, there's this little Spotlight search box. And then automatically the focus is in that search box. So then whatever you type appears in that search box. Then you type terminal. So terminal.app is like the Mac OS X's, what do you call it? Their shell. All right, so then we type terminal. Then Spotlight finds terminal.app. And then if we press return, then what happens is the terminal.app launches. And then the focus is automatically in that in terminal.app. And then we can type this sequence of characters, exec, bind, shell, all that. Of course, IP will be replaced by the attacker's IP address, and port will be replaced by the attacker's port number. So if you do this and then you press return, that shovels a shell right to the attacker. You can have a netcat listener on that IP address and that port, and boom, you just have control of the machine. So, there's a reference to a NeoHapsys blog entry if you want to know exactly how all that works. So, okay. So clearly if an attacker has control of your keyboard, that's a bad thing. They can pretty much do whatever they want with your machine. And one thing is, a fair number of Mac users, they use this product, a Little Snitch. It's this personal firewall. And by default, the thing is the selection is such that it allows the outbound connection. So this is easily bypassed. We just, in that keystroke stream, we just add an extra return. Boom, Little Snitch doesn't do anything. All right. So what this means, so if we have control of the keyboard, what we can do is say, we have control of the machine. We take over the keyboard, and then, whenever the machine boots up, it signals to the keyboard, I'm still in control. But if at some point we find out, we're no longer in control, the keyboard realizes, somehow the malware on the host computer disappeared, then what it can do is the keyboard can say, I need to send control back to my master, basically. So what we can do is we can persist the rootkit if we have control of the keyboard. And so this picture is of this guy. His name in real life is Terry O'Quinn. So if you see the TV show Lost, you know that this is some guy who just keeps coming back from the dead. Anybody see that TV show? It's a really crazy TV show. Okay. So if we have control of the keyboard firmware, we can do rootkit persistence. Okay. So let's look at the current lineup, Apple's current lineup of keyboards. So right now, if you want to buy a keyboard from Apple, there are 3 of them that they sell. So about 2 years ago, they first came out with these thin aluminum keyboards, these very thin things. And so they had a USB and a Bluetooth version. And the USB version costed $49 and the Bluetooth was $79. And then just recently, a couple months ago, they came out with another USB keyboard that's a little bit slimmer than the old one. The old one had the numeric keypad and all that. And so now they have the slimmer one that has basically the same layout as the Bluetooth keyboard. So currently Apple sells 3 external keyboards. And out of these 3 keyboards, I believe that the top keyboard is the one that's most widely deployed. That's my belief. I mean, it's been out the longest, and it's the cheapest. And it comes default with when you buy a Mac Pro and iMac, you can get one of these $49 keyboards for free. I believe that's how Apple is currently doing business. And if you pay additional money, then you can get the Bluetooth keyboard. So out of these 3 keyboards, I believe the top one is the one that's most common. So that's the one that we're going to focus our attention. It's the most widely deployed, and basically we want to own as many people as possible. All right, so I have a picture of a dog with that particular keyboard, and the dog seems to approve. Okay, so when this keyboard first came out back in about 2 years ago, the thing is it had bugs. Apple once again doing their thing of releasing products before they're fully tested, and so if you go to on Apple's site, they have like a discussion board section. So people complain about all these the problems they have with Apple products. So some guy was complaining that there's some problems. Some modifier keys sometimes seem to skip or not be recognized and so forth. He had various problems. So this guy complained, and when was it? What's the date of this message? November 2007. And then there's another guy also had a complaint. He had an aluminum keyboard, and he's like, "Oh, mine seems to miss like 1 in a dozen keystrokes." So sometimes Apple also has this habit of removing discussions from this bulletin board. But I was able to find these, and so I'm showing them to you. So when the keyboard came out, it had problems. Some users experienced problems. So, all right, so the next section is about the firmware update that Apple issued to address these problems. So they issued this aluminum keyboard firmware update 1.0, and this was issued in April of 2008. So you can go to support.apple.com and download this thing. So if you go to Apple's site and you download it, it's like just between 1 and 2 megs. So okay. So if you use Firefox and you download it, so you save it to the desktop, then you get this .dmg file. And if you're not familiar with Mac OS X, this .dmg file, you double click it, and then it creates this little volume thing. And then within this volume, there's there's a file, there's a .pkg file. What I've done is I've included the SHA-1 hash of the file that you download from Apple, just in case Apple removes the update, or if they change the update on their website, just in case you can see that you're using the same one that I used to do this work. Okay, so so this is like the firmware update that you can download from Apple. And if you have a Mac and you have this keyboard, yes, a question? Yeah. What do you mean? Sorry. The picture that are you looking at that picture? That picture is not correct. Like Apple's website isn't. I don't know why they have this. The thing is, this firmware update. If you look at how the firmware update works, it actually has an updater for the top 2 keyboards that I showed on a previous slide. Yeah, ignore that picture. Like Apple just screwed that up. Yeah, what this update does is it can update the wired aluminum keyboard and then the Bluetooth keyboard. That's what this thing does. Yeah. Yeah. Thanks for the question. Okay. So most likely, so if you have, suppose you have one of these aluminum keyboards, and then you download this thing. You download that thing and you double click the .pkg file, and if you practice good internet hygiene and you apply your patches and everything, then what happens is the installer says your keyboard does not need this update. It says it already has the updated functionality. So apparently there is some mechanism in this installer to check whether or not whether or not to actually apply this update. So, but it doesn't matter. Whatever checks they have, we can get around that. That's no problem. So if you have the Xcode tools installed on your machine, there's a application called the Flat Package Editor, and what that does is it allows you to look inside these .pkg files, and so so within the .pkg file, there's more .pkg files, and within one of those .pkg files, the top one, that one handles the wired keyboard, and so there's this file called payload. And just as an aside, also there's some tool, command line tool that Apple has, like lsbom, to list these what's inside a .pkg file. I just use the GUI tool. So what we'll do is say, in order to extract this payload file out of this .pkg thing, what we can do is we can click on it and then drag it to the desktop. So if we do that, we drag it to the desktop, and then we double-click that payload file. That thing, we'll just let the Finder extract that thing for us. And what it does is it creates a directory called Applications, and then within Applications, it creates a directory called Utilities, and within Utilities, there's an Aluminum Keyboard Firmware Update application. I mean, what the installer thing does is it moves this thing to the root directory of your machine and then does it, and then because Applications and Utilities already exist on your machine, then this Aluminum Keyboard Firmware Update gets installed into that directory on your machine. But since I copied it to the desktop, it creates it on the desktop. Okay, so now if I click on that application, that Aluminum Firmware Update utility, this thing also checks whether or not the firmware needs updating, because you don't want to do unnecessary firmware updates. Flash memory has limited lifetime. You can't just constantly write to it. It will get worn down. So this thing also checks if the keyboard needs updating, and it says, oh yeah, if your keyboard is already updated, puts up this dialog box, your firmware is up to date, and there's no other option. You got to quit. Okay. So in that case, what we want to do is we want to look at this Aluminum Firmware Update application. So and in Mac OS X, these applications, they're actually directories. So what we can do is in Finder, we can right-click and do Show Package Contents. So that .app is treated as a single entity. So there's all this stuff inside, and there's a contents directory, and then within the contents directory, there's all this other stuff. And in terms of general reverse engineering on Mac OS X, I highly recommend Cameron Hotchkiss' talk at Recon. So you can see that there's a Mac OS directory, and then there's a resources directory and all this stuff. And for Recon, the website is recon.cx, not recon.com. You don't want to go to recon.com. Okay, so if you look at the stuff, so now what we want to do is we want to look at what's inside that resources directory. So if we look at inside there's all this stuff. There's all this, the localizations for all this, the different languages and stuff. And okay, so what we're going to do is we want to look at the actual binary is in Mac OS inside that directory, and it's called Aluminum Keyboard Firmware Update. So that's what we really want to look at. So if we look at the first 16 bytes of that thing, we see there's a magic number of Cafe Babe, and Cafe Babe is the magic number for Java bytecode. And for some odd reason, Apple decided to use the same magic number for their fat universal binaries. So this thing, yeah, it's a fat universal binary, and it has binary code for both Intel and PowerPC. And Apple does have a sense of humor. They have this tool called LiPo, which can be used to take a fat binary and then extract out the whatever architecture you're particularly interested in. But what we're going to do is we're going to look at the x86 binary. It's going to be easier to look at. Okay, so one thing is one tool that Apple has for looking at devices that are attached to your computer is called I/O Registry Explorer. So we can use that to say we plug the keyboard in and we see it on the USB bus, and there's all this information about the device. So, so what I did was I took a keyboard that's been updated and one that hasn't been updated, and then just compared the two. And if we do that, then the updated keyboard, they both have a vendor ID of 5AC. That's Apple's vendor ID, and they both have a product ID of 220. But the updated keyboard has a BCD device of 69, and the The non-updated keyboard has a BCD device of 67. So BCD device is just binary coded decimal for the device's release number. Okay, so this is like a very easy way to just scan the USB bus and see whether or not the keyboard is updated or not. Okay, and if you look at the output of USB view on Windows, that I have to tell you the truth. I'll tell you the truth that IO Registry Explorer tool like drives me nuts, and it doesn't give me the information that I necessarily want. So like for a USB device, one of the things you want to know is like the not only just like the device descriptor, but you also want to know about like the endpoints and stuff. So for these USB keyboards, it has 2 interrupt in endpoints, and that's the information. Every USB device has a control endpoint, endpoint 0. Then it has 2 interrupt endpoints. So like in terms of polling, the B interval value is a 10. And then the first interrupt in endpoint has the packet size is 8, and the other one is 1. Okay. So yeah, you could also use this tool that Apple has called USB Prober to get the same information. And yeah, if you don't know what those values are, like I'll explain exactly what they are. All right. So in order to disassemble that binary aluminum firmware update, I use this tool OTX. So the output is much better than the output you get from OTool. And you could have also used IDA Pro. I don't have a license for IDA Pro. And in order to edit the binary, I use this tool, EDE. Okay. So before we kind of get started, I want to say a little bit something about the legal situation we have here. So from the DMCA, I'm just going to read right from the law here. It says a person who has lawfully obtained the right to use a copy of a computer program may circumvent a technological measure that effectively controls access to a particular portion of that program for the sole purpose of identifying and analyzing those elements of the program that are necessary to achieve interoperability of an independently created program with other programs. So I believe that the reverse engineering that I'm about to do is completely legit. The reason is that, so I've written a Trojan, like malicious code, and I want to make sure that it's interoperable with Apple's keyboards. So I don't believe that this is completely legit. This is for interoperability. That's why. So there's no DMCA violation here. Okay. So that aluminum firmware update thing, whenever we ran it, it immediately put up this dialog box and said, "Oh, your thing is already done. You don't need this update." So you look at it, and if you have some experience with Mac programming, like say there's this delegate method, application did finish launching. So and another place that they could also do it is like awake from nib. So this thing runs and prior to doing event processing, and here this is where it's doing stuff. And so if you disassemble and you look at it, so it checks like the OS version, make sure that you have 10.5.2 or higher. It uses the IOKit library. So the IOKit library, that's the the Apple's like hardware interfacing library. So it queries like the USB bus and it looks for devices that have a vendor ID of 5AC and product IDs, 222, 221, 220, and 228 in that order. And then it also checks the validity of this file that's in the application bundle, like in the resources directory, this KBD underscore thingamajig. And it checks the validity of that thing using a function called CRC32. So CRC32 is, as part of this, is this method that Apple has. And just for fun, why don't we take a look at this function CRC32, because it's actually pretty hilarious. I mean, it really is hilarious. So we have the use. Yes. Go ahead. It's fine. Yeah. Those that doesn't match the Bluetooth, and they don't. I don't know exactly what those other IDs are. Oh no, I believe that this works on pretty much the underlying ideas work on just about every keyboard that Apple manufactures, actually. But okay. So we're looking at this the disassembly of the CRC32 function. So we have the usual function prologue. We're saving the ESI EBX, allocating space on the stack, and so forth. And the context is that this CRC32 method is called with a pointer to like an NS data object, and that NS data object, there's a class method that that is I already forgot the name of that class method, but it's basically passed. The argument is the that file in the resources directory, this KBD, the firmware image file, basically. And so if you know how like Objective-C, there's message passing and stuff. So the first thing is you send a length message to that thing, and the values is saved in ESI, and then you send a bytes message to that thing, and then that is saved in EBX. So ESI has the length, and EBX has the bytes to this file. You see that the ECX and EDX are cleared, and then there's this loop here, and so you see that EDX starts from 0 and is constantly being incremented, and then basically the bytes of the file are being accumulated into ECX, and that's all that thing does. The ECX is constantly adding up the bytes of the file, and then it's being returned. So is this CRC32? No, it's not. I mean, not even close. So clearly this engineer at Apple did not know what CRC32 is. I mean, this is just wrong. So, okay, so if Apple can't even implement this, the thing is the polynomials used in CRC32, there's different polynomials you can use, but Apple just screwed that up. You can just look at it and it's obvious they screwed it up. Okay, so the thing is, so this aluminum firmware update thing, it does, it puts up that message, and what we want to do is we want to disable those version checks. We need to patch the binary. So then, there's this other inside this my main controller class or something. So we got to patch this thing. So the patch is, see that red thing? We see those two red lines. Those instructions, we make them both unconditional jumps. Then we have this other thing, like the show instruction thing. We know up that last conditional jump. And if we do that, then the updating thing is, well, it no longer does those checks. And then this is the message that you would see if you had an unupdated keyboard and you plugged it in. So then there's just one option, update. And okay. And all right, so the only thing is if you click that update button, then it gives you an error. It says, the firmware cannot be updated. So there's another place where the firmware version is being checked. So now what we want to do is we want to go into the resources directory. We want to look at the NID file. So back a while back, for applications that were created using the Xcode suite, the user interface stuff, that was stored in a .nib file. And then when Xcode 3.0 or whatever, the one that was pushed out in last fall, they changed those files to .zip files. So this is an older application, so it still uses .nib. So with that thing, it encapsulates all the user interface, menu items, and all that stuff. Okay, so we can the tool that a developer uses to create that thing is called Interface Builder. So we can just pull that thing out. We can just open it in Interface Builder and see what it is. So you see the user interface there, and you see the update button. And then we can see whenever you push that update button, you see right away exactly what is the code that's executed. And this is a very simple user interface. There's just one button. So, and you can see that it's the resolution of this. I can barely see. It's so it's do update in my main controller. So okay. So whenever you click the update button, that's the method that's called. So yeah, so that NS button, the target outlet is set to that class. The action is set to that method. So what we do is we just immediately go to that method and look at the disassembly. And we see that the machine checks that the machine is plugged in. So the thing is, you don't want to be doing firmware update. Or say if you have a laptop and you're running on battery, because if you have power problems, that can be bad. If the firmware update is interrupted. And then the thing asks for administrator privileges. And it turns out you don't actually need administrator privileges. And then what it does is there's actually another binary in the resources directory called HID firmware updater tool. And this thing is called twice by that Cocoa application. So the first time it's called with the arguments like parse, and then that firmware image. And what that does is that just checks whether or not the thing is valid. And then it calls it again with those arguments. And the second time it's called, that's when it does the actual updating. So, and if we look at this tool, it doesn't really have much symbol information. And this is the third place where the keyboard, the version is checked. And it refuses to do anything if it finds that the BCD device of the attached keyboard is hex 68 or higher. So we got to change that. If you want to see how this whole process works, we have to disable this check. So this is like a disassembly of some part of that tool. And then if we no op that jump above instruction, then we're able to, even if the keyboard has been updated, we're able to reflash the firmware. So let me give a quick demo of how that works. So, actually, you know what? What's going to be seen will actually be seen when I do other stuff. So I'll show it. I'll show you exactly what it looks like in another thing. I guess I'm going a little bit slower than I expected. Okay, so the next section is I'm going to do some analysis of how this whole thing works. So if you look at this file that's in the resources directory, this KBD, hex 69, hex 020, 0220 file. If you look at the first 32 bytes of this thing, that's not something that you can easily recognize, right? You don't know what that is. So what Apple did was they obfuscated this file. So, but the thing is, if you follow how this whole process works, so Apple has this update, it sends this obfuscated firmware to your Mac, and then, but what the updater does is it unobfuscates the firmware image on your machine, and then it pushes the unobfuscated firmware to the keyboard. The keyboard itself does not do deobfuscation. So that's what Apple did. So what we can do is we can use this HID firmware updater tool to unobfuscate Apple's firmware update. And so the plan is, so we've owned this Mac, and so then we take Apple's obfuscated firmware update. What we're going to do is we're going to modify it. So we're going to modify the unobfuscated firmware update, and then we're going to send, put our Trojan in there, and then send it to the keyboard. That's our plan. Okay. So then when we do that, then the keyboard also gets owned. So we own the Mac, then we own the keyboard. So okay. So now let me say a little bit about the obfuscation. So if A is this 83-byte sequence and B is that 53-byte sequence, then the deobfuscation algorithm is that. And clearly this is not like this engineer clearly did not know cryptography. And then in addition to this, there's further obfuscation, but it doesn't really matter. It's like dealing with packed malware and stuff. It's not really worth the effort to try to figure out exactly how the packing algorithm works. You just wait for the malware to unpack itself in memory, set an appropriate breakpoint, and then look at the completely unobfuscated thing. So then there's kind of a truism in this industry about not doing security through obscurity, but Apple didn't get that memo. So this is a screen grab from Office Space. So, okay. So what we can do is we can very easily, using this HID firmware updater tool, we can very easily pull the unobfuscated firmware out of memory. So we just attach a GDB to it, set a breakpoint at that address, run it with that argument, and then by the time that instruction is hit, then the firmware has been completely unobfuscated, and then we can just dump it to disk. So we can dump it to a file, dump that bin for that range of addresses. And if we look at the first 73 bytes of this file, that's what it is. And it turns out that this file has a very regular structure. So if you look at these little red parts, it turns out that there's these 3 bytes followed by 32 bytes, 3 bytes followed by 32 bytes, 3 bytes followed by 32 bytes, and that's how the whole image looks like. And what happens is those things that are in red, those are like block addresses. That's what it is. The block size of the flash is 64 bytes, and then these are kind of a half block at a time. Okay, So in order for the firmware update to work, what it does is there's a bootloader. And so like the keyboard, it doesn't have an interrupt out endpoint. So, so it has to use the control endpoint, right? In USB, everything is host-centric. And an in endpoint, the data comes into the host. You can't use an in endpoint to send data from the host to the device. So it has to use a control endpoint. And if you look at the disassembly, that function 20C3 does it. And what it does is it calls this method device request in the IO USB device class. And okay, so what we're going to do is we're going to look at this. So we set a breakpoint at the appropriate place, and we look at the arguments of this function device request. So we see that's what the arguments are. This is what that IO USB dev request struct is. So we're going to pick that thing apart. So if we go to opensource.apple.com and we download the source to this the USB stuff, you see this struct for IO USB dev request. So the first byte is this BM request type. Then the next one is this B request. And if you look at the USB standard, this is a set report. So, and then if you look at this W value, so that 2 bytes. So we're sending a feature output report. So, and then this is the number of the interface, so, the endpoint 0. The 0 is always the control endpoint. Here's the length of the report. So it's just 1, right? And then we look at the actual data. So you have a pointer to the data, and we look at it as just A. That's all. A as an apple, I guess. All right. So then, okay. So in order to put the keyboard into bootloader mode, so then what we do is we have to send this feature set report, and this is something that Apple cannot hide. We can have a USB sniffer in line with the keyboard and the host. We can see all of this. I just happen to do it in software. So okay. So whenever we do the firmware updating process, what happens is when we run that HID firmware updater tool, the keyboard is first attached, and then when you send that thing to the control endpoint, it drops off, and then the keyboard re-enumerates as this bootloader. So, okay, so you can see that this bootloader, it has an interrupt in endpoint and then an interrupt out endpoint and then the usual control endpoint. Okay, so then what we want to do is we want to look at the first 64-byte packet that's sent to the keyboard. When I say packet, I really mean the first 64 bytes that are sent. It's obviously because of this is a low-speed device. It has to be broken up into smaller things. You can't have more than 8 bytes sent at a time for low speed. So this is the first 64 bytes that's sent to the keyboard, and we'll completely understand exactly how all this works. So we can determine the commands of the bootloader password, the format of the data, how the checksums are calculated, and the return codes that the keyboard gives us. So, and you might want to spend just a second trying to guess what the bootloader password. It's so simple. You'll be shocked. So if we look at the first 2 bytes of that packet, this is FF38. That's enter bootload mode. And if you look through the binary, you can see that there are these other commands: write to flash memory, verify flash memory, exit bootloader. So then we look at the next 8 bytes. That's the password. 0, 1, 2, 3, 4, 5, 6, 7. So that's the password that Apple used, and it's constant for everything. That's all. And then you look at the block number. So the thing is, each block is 64 bytes on the flash, but we have to send it a half block at a time. So then the block number is sent in that field there. And then we have to indicate, since we're sending 32 bytes at a time, we have to indicate whether or not it's the bottom half or the top half. And then the actual data that's sent, that's 32 bytes, and that's where it goes. So, all right, then we have this checksum. Each packet has a checksum, and all it is just the values added together. Okay, and then if we look at the stuff that's sent back, the return code is just that first byte. So here we have a return code of 20. And then if you look through the binary, we can figure out exactly what the other possible return values are. Device did not respond. You say you try to write to a block that's flash protected. We make an error in the checksum. That hex 20, no error, or an invalid command. And then at the very end, so each one of these packets has a checksum. And then if we look at this look at like, say like this, if we keep adding up like those 32 byte blocks and then add up the whole thing, then we get 4E41B. There's like an application checksum also. In addition to checking each packet, there's another checksum. And what that is done in the very last write packet, the second to last and the third to last bytes are used to store the final checksum. So you mod it by, take the last 2 bytes and then you store that in big endian format. So this is how the whole updater procedure works. And you can see that there is no cryptographic signature, none. And this is just nothing. So this is pretty bad. So if we want to, so now we understand exactly how the updater process works. If we want to be able to exploit this, we have to understand what the underlying hardware is. So let's look at the inside of the keyboard. So here, there's a tiny little circuit board, and you can see there's a hub chip, there's a serial EEPROM, there's a microcontroller. So a slightly closer up image, and you can see like that ribbon cable and stuff. If you look at this previous, you see there's little white thingies on there. The keyboard has no screws. It's sealed with like glue and stuff. It's like a single thing. It's actually kind of hard to take apart. Okay, so now let's look at that this chip. So this is like I guess a 48-pin SOP package. So what Apple uses for their microcontroller is this Cypress chip. It's a low-speed USB controller, Harvard architecture, 8-bit, and so it has just 256 bytes of RAM and 8K of flash. And if you try to ask Cypress for a sample, you try to buy this chip, it doesn't seem available anymore. And the data sheet has somehow disappeared from Cypress's website. But I was able to find the data sheet online. Okay, so let's quickly look at the architecture of this thing. So it has a 16-bit program counter. You can't have an 8-bit one, obviously, otherwise you can't address all the memory. You have an 8-bit accumulator that's used as a general purpose register, and then you have an 8-bit stack pointer. The stack on this architecture grows upwards. And then we have an index register that's 8 bits, and you use that to like index into various things. And you have like a flags register, that thing is 8 bits. You have a bit for like global interrupts. Then you have like 0 flag bit, carry flag bit, and they work in the usual way when you do like logical and arithmetic operations. And this thing has also a supervisory state bit. And with that, there's a special mode for writing the flash and stuff, that the chip can write its own flash. So there's a special kind of mode for that. And in order to read the flags register, you have to read it through F7. And if you want to set or clear bits in it, there's special instructions that the chip has for that. So, okay. So let's look at the interrupt vector table for this thing. And so you can see all these various entries. You know, the program starting there, the power on reset, low voltage detect and stuff. So whenever like these appropriate interrupts occur, then those 4-byte things are you're vectored into there, and then you can call your service routine. Okay, so this microcontroller has this like supervisory system call, and it has a number of interesting functions. It has these. It has the ability to do this stuff, and what makes this whole talk possible is that there is this write block method. And what that does is the microcontroller can change its own flash memory. It can change its own program. So, okay. And so since this is a USB device, the natural thing is we're also interested in the serial interface engine. So the serial interface, whenever you're developing a USB application, you have to know like what does the serial interface engine take care of and what does the firmware on the chip take care of. So the serial interface engine, it takes care of translating, formatting data. It does like the CRC checksums for us. You know, CRC, remember, that's for interrupt, bulk, and control endpoints. The isochronous, there's no error checking. The device address checking, in USB you have 7-bit device addresses. So whatever, there's a register where you have that, and then like whenever data comes in, it only gives you the stuff that's for your device, that address that's set during the enumeration. And then the kind of like the third part of a USB transfer, you have to do handshakes. So the serial interface engine takes care of that for us. And then like the very first part of a USB transfer, the setup in out tokens, this thing identifies that stuff for us. We don't have to do that. The firmware doesn't have to do that. And then whenever you have like in data, you have the serial interface engine will parse that and put that into the endpoint buffers for us. And then like the data toggle bit, like the sending and updating is taken care of, and bit stuffing and unstuffing is taken care of. Because in USB it's differential signaling. So on the like power, ground, and D plus D minus, and D plus D minus is differentially signaled, non-return to zero inverted. And because in order to avoid clock skew between the host and the device, the USB doesn't allow more than 6 consecutive ones to be sent. So then, when you send more than that, then the host controller or whoever the sender is, automatically stuffs a 0, and then the device says, oh yeah, there's 6 consecutive ones. We have to unstuff that 0. So that pain in the ass stuff is taken care of by the serial interface engine. But what the firmware has to do is it has to do enumeration. So enumeration, that's the process where when you have like a computer and you plug in a USB device, like the host computer is interrogating that thing to figure out, to learn more about the thing. So, and then we have to take care of like putting the data into the FIFOs, the endpoint buffers. And like say if there are like in USB, if you have the time in USB, the 1 second is divided into, the time is divided into periods of 1 millisecond, and those are called frames. And if you have like 3 or more consecutive frames where there's no activity, then the device will slowly go to sleep. And so that, we have to take care of that. And the verifying selecting data toggles, we have to do that. And also one of the chips on that board is this serial EEPROM from Microchip. It's a SPI chip. They could have very well used something from Atmel or ST Microelectronics. It's a very commodity part. And then there is this hub controller. So this USB 2.0 hub controller is also from Cypress, and it supports up to 4 ports, although Apple only uses 3 of them. And that serial EEPROM just on the previous slide, it configures this chip. Okay, so a rough schematic of what the keyboard is. So we have the upstream connector to the host. We have the hub and the EEPROM connected to the hub. We have like on the side of the keyboard, there's these 2 USB ports. One USB port is not used, and then in one of the USB ports, the keyboard is actually plugged in. So this keyboard, it's actually a compound device. It has a hub, keyboard is plugged into the hub, and then there's 2 free USB ports. Okay, so then in terms of visual indicators, there's only 1 light emitting diode on this keyboard. So what we can do is, we can figure out exactly how to, we look at that ribbon cable and we take a coin cell battery, we can figure out where the leads of this, of that LED are. So this is a schematic. So you can see that in order to turn the LED on, we want to go, it's active low on pin P2.7. Okay, so so now what we're going to do is I'm going to be talking about exploitation. So so if you look at that register, like P2, this is where P2.7 is. This is what we want to, if you want to control the LED, this is how we do it. Okay, and in order to control like whether that's like whether or not it's output or input, there's another configuration register, that's the 15th register, or hex 15 register. So what we want to do is we want to go through the firmware image and we want to find instructions of this kind. Like you can see that there's a couple ways in which we can set the value, but it turns out that if we look at instructions of the form move, register, hex 02, in an expression, we can change how the LED behaves. So we want to look for 6202 in the firmware image. So if you're looking at the firmware image, the first unobfuscated block is this. So this is a relocated interrupt vector table. And if you kind of go toward, you can see that if we match it up to what the entries are, we have this. And if we go to the end, then there's like where the program memory starts. There's an immediate jump to 300. So we want to go through the firmware image in memory and find it. And so there's this painful, so we see this 6202 there. And there's, whenever you're doing this stuff, there's this painful conversion between like block addresses and actual addresses. So in the firmware image, there is like block addresses. So like the blocks are, so this block for hex 300 is block number C. So, the blocks are 64 bytes in length. All right, so then we just immediately, like it jumps to hex 300, so we can start disassembling from there. So we have that instruction, then we have this instruction, so we're putting 0 into F8. So when I say reg 32, that's the register 32, and then the left bracket F8, right bracket, that's memory location F8. Memory location F9, We move A3 into the accumulator. We swap the accumulator and the stack pointer. And here we move 80, hex 80 into register 02. So this is where Apple has set the initial state of the LED to be off, right? It's active low, so it's been turned off. So we're going to alter this instruction and we'll change it to, what we'll do is we'll turn the LED on at startup. That's what we'll do. Okay, so we have to be kind of careful. Because it was changing like F8 and F9, those are also used by the supervisory system call, and we don't want to have problems. But here, the supervisory system call is not being called, so we don't have to worry about it. And say again. To disassemble. Oh, I wrote my own. Yeah. I had to, the thing is, Cypress, they don't have a disassemble, so I had to write my own. Yeah. Okay. So the thing was, I remember like in the very last write packet, there's a final checksum. So we're replacing 80 by 0. So the application checksum, it goes down by hex 80. So we have to subtract 80 from 4E41B. So the E39B, the new checksum is E39B. Okay, so this is the exploit. So we'll, so now let me just go ahead and run it. Okay, so hopefully this will, let's just do this. All right, so we want to attach. So this is the patched HID firmware updater. So okay, so let me go to the. So I'll set the. Whoops. I can't see anything. Oh, okay. That's because it's over there. So I want to. Actually, let me just bring it over here so I can actually see it. So, so I set the breakpoint, then I run it. Oh shoot! Let me attach the keyboard first. Okay, so I attached this thing here, and then run it. Then what I'm gonna do is I'm gonna make some modifications here. Okay. So this is what the this is what the firmware updater tool looks like. So even if we hadn't modified the firmware in memory, this is what it looks like. So now it's across the USB bus, it's updating the firmware. Okay, so then we'll wait for it to finish. Okay. Then now I'll go to photo booth and let's just see if this thing actually works. So look at this. So I'm gonna unplug it and then plug it back in. So wait, what the heck? Oh, it just locked up. Oh, so photo booth seems to have. Sorry, photo booth seems to have some problem. Yeah, sorry about that. Yeah, you won't be able to see it back there. Basically, what happens is rather than the LED being off in the beginning, now it's on. So if you want to see it afterwards, you can come on up. Yeah, sorry, I wanted to use this web. Yeah, okay, let me do that. Okay. You ever see that? The LED went on. Okay, so we can. All right, so we can completely control the. We're able to completely control the LED. So the thing is, that's very benign. That's nothing. So the thing is, if you're interested in controlling the LED, the most significant bit of that memory location is used to control whether or not the LED is supposed to be on. We can completely decouple the LED from the caps lock functionality. We can make it just flash on and off, do whatever. Okay, so now I'm going to show that we can alter enumeration. So we have this, if we look through the firmware image at this location, and this is like the address. So you can kind of parse it, look at the USB standard and parse it. So we see like the supported language, this is an English keyboard. We have like the size of this, the manufacturer string. So it's sort of Pascal style. So it's hex 16, the string descriptor. And then we see in Unicode, we have A, P, P, L, E, comma, space, I, and C Inc. So what we'll do is we'll change Apple Inc. The Inc. is finished on the next half block. So we'll change that to owned. So this is the exploit that we'll use. Okay. In fact, let me sorry, the keyboard's still attached. Now I'm just going to paste that all in. Okay, so now I'm updating the firmware. What I've done is I've just changed that Apple to owned. So just have to wait a little bit. Okay, so now let me pull up IO Registry Explorer. So now we look at this keyboard, and then we should see down here see that. So we're able to change the USB vendor. We're able to change the vendor name. Okay. So we can control any part of the enumeration process, vendor ID, product ID, whatever. I'm just showing I'm just doing the vendor name. Okay. So now let's continue. So that's also pretty benign, right? So if that demo didn't work here, this is also the same thing. So if we look in the firmware, like for this microcontroller, 30. By the way, how much time do I have? It's 15 minutes. Okay. So in the middle of the hex 30 is the halt instruction for this microcontroller, and in the middle, see, this is the firmware image. And everywhere there's red, there's a halt instruction, and everything else is blue. So in the middle, there's this huge sequence of halt instructions. That's just free space. So we can just stash whatever we want there. So just as a quick reminder, this is just straight from the USB standard of how interrupt transfers work. So we have an interrupt in endpoint. So only the left side applies, and what's shaded, that's what the host does, and what's white, that's what the device does. So the host sends an in token to the keyboard, and it's constantly doing this. Like that B interval value, it was like A, so latency is guaranteed to be within 10 milliseconds. Like at least once every 10 milliseconds, the host queries the keyboard and says, do you have something for me? And if you don't have something, then the keyboard sends back a knack. But if it does have something, then it sends data, and then the host sends back an acknowledgement. Just a quick reminder of how interrupt transfers work. So how do we intercept keystrokes that are typed by the user, and can we send our own keystrokes back to the host? This is very easy to do. And this is just USB, and we can just use the endpoint buffers. So the keyboard uses the first interrupt endpoint. So just to make it clear what's going on here, this is like I took the keyboard, plugged it into Windows Vista box, and I used a USB sniffer, and I typed the enter key. So you can see those two like sequences of 8 bytes. You push the enter key so that you see that hex 28, and then you lift the enter key up, then all zeros are sent. So that in the very beginning, I was talking about sending like a sequence of commands like activate spotlight and send terminal. This is exactly what you want to send across the USB bus in order to do this. So you can see how it's very simple right here. Hold down the command key, hold down space, lift up the command key, lift up the space key, that sends command space, push down T, lift up T, and so forth. So, okay. So now what we want to do is, in terms of Apple's firmware, we want to look at the routine that copies stuff to the endpoint buffer. Like this is crucial for exploitation. So this is the routine that does it. It's at 1EF0. So like the X register points to the stuff we want to copy into it. The endpoint number we put into memory location 32. And memory location 33, we put the number of bytes to copy. And I wanted to put a comment to 22, but I must have forgotten. Yeah, sorry about that. But this routine, I don't really have enough time to really dig into it. But this we can treat this like a black box. This is what we give it a memory location. We tell it the endpoint. We tell it the number of bytes to copy, and it just copies it to the endpoint. So that's the whole routine. So the next example, what I'll do is if you remember back when the presidential election 2000, there was a really disputed election, and when Clinton left office, what a lot of the people in the White House did was they took all the keyboards in the White House and they removed the W key. Does everybody remember that? They literally removed every W key. So we can do this also, but we can do it in firmware for the Apple keyboard. So let me demonstrate that. So first, let me demonstrate on this keyboard that the W key works. So you can see, let me see that, like the W key is working and everything. So, okay. Okay, so now we're going to update the firmware. And what we're doing, in fact, sorry, I didn't even explain how this whole thing works. I'll explain in a second just how this thing works. Let me just first do the firmware update, and then I'll show you that the W key has stopped working. So now, if you look at it, I'm pressing the W key, and it no longer works. So I'll explain how that works. So remember, I just told you about this routine that copies things to the endpoint buffer. So what we want to do is then we want to look at routines that call this routine. We want to look at the routines that call 1EF0. So this routine, starting at 0T51, every single time a key is pressed down and lifted up, that thing is called. And so what we can do is we can modify this thing. So this is what the firmware looks like originally, the start of that routine. And in the middle of that, that free space with all the halt instructions, this is the original firmware on the left-hand side. Then what we'll do is at the top of 0D51, we're just going to put a jump right into the free space. So we do a jump to 1000. And then in 1000, what we do is we put our own little code. We're looking at, it turns out that the 67, that's exactly where the keystroke is in the buffer that's, in the buffer that backs the endpoint buffer. So if it turns out to be 1A, if you look at the HID usage tables, that's exactly the W key. So if it is, jump not 0, so if it's not W, then we go down to 1008. 1008, if we look at that, 1008, so all I did is I just copied that code from 0 to 51 down there. So we just do what was originally going to happen. However, if it is 1A, if the W key is pressed, we just write 0, we just override it with 0. So that disables the W key. I mean, I can completely disable the keyboard, actually. I'm just doing this as a kind of an example to pay homage to what the Clinton staffers did. And so, so I've already disabled the W key. So that's the exploit. So, so I just gave you a demo. But, so those first 3 exploits, those are kind of not a big deal. And, but what we can also do is we can also intercept the keystrokes and store them. We can also do that. So here, this is the exploit that I've written. So it's the same setup as before. We change that 0D51, jump to the free space, and then we copy our code here. So the way that this thing works is I first want to check whether or not the key has been lifted up. That's what that first comparison does. And because I'm using the X register, I push it to save it. And then 28, hex 28, that's the return key. The usage from the HID usage tables, that's the code for return key. And whenever the return key is pressed, what I do is I store temporarily store keystrokes in the register space for like the endpoint 2 buffer, and so I'll store stuff there. And when I press return, I'll take stuff out of there and send it over the bus. But whenever the user doesn't press the return key, then I'll actually store those values. And here I'm using this register space because then it's a little bit harder for somebody to modify this code and create a full-blown keystroke logger. And I'm using the enter key to recover the keystrokes because that way, if somebody uses this on somebody, then it's obvious there's something wrong with the keyboard. So let me give you an example of this. So here, this is a firmware keystroke logger. So this is the whole code. So let me give you a demo of this. Where's the? Oh, there it is. Okay. So so now it's updating the firmware on this thing. Oh, it depends on where you want to store them. I have a slide about just exactly that. Okay, so now I've updated the firmware. So now this keyboard is owned, basically. So I'll type, I don't know what people want me to type. I'll type, I'll just see it doesn't matter. It doesn't matter. So suppose I type key, W-E-R-T-Y. And then now, remember, I use hex 28. That's the return key. So I can press return. Everybody sees that? The keystrokes that I had just typed, I'm retrieving. They're stored in those registers. So we can install, because of this, there's no cryptographic signatures, we can install a keystroke logger right onto the keyboard. So, okay. Oh, whoops, let me start this thing up. Okay. So this is a proof of concept keylogger. Okay, and I've deliberately neutered. I use the return key to retrieve keystrokes. That way, if somebody takes this code and uses it, then it's not a really effective keystroke logger. And if you store things in memory, you can't get like a whole lot of keystrokes. You can store like a couple dozen keystrokes. But if you decide that you want to write, remember that there's all that free space in the middle of the firmware image. If you want to, you could also take keystrokes and save them and store them there. So you could store like probably up to about 1,000 keystrokes directly in the firmware of the keyboard. And so this is useful. So you own the box and you realize they use PGP full disk or something, then you can steal their whole disk encryption key. This could be used to do that. So do we need physical access to retrieve the data? No. There's this academic paper by Matt Blaze at Usenix Security. In order to exfiltrate data out of a keyboard, what they do is they use timing delays. I haven't implemented this. This is just something kind of theoretical. And so don't use Apple keyboards in your data center because, say suppose you have a box and then there's like this KVM switch. And the KVM switch is on your box. You control that. You update the firmware on the keyboard. And then the sysadmin changes it to another machine. Then you can send out your own keystrokes to another box. Okay, so what about the MacBook and MacBook Pros? Here, what I've been doing is I've just been talking about this external Apple aluminum keyboard. So what about the portable keyboards? And Apple has also issued firmware updates for those. And if you look at a MacBook, MacBook Pro, those internal keyboards, those are actually USB keyboards. On the USB bus for an Apple portable computer, you have the iSight camera as a USB device, the Bluetooth adapter is a USB device, the infrared adapter, that's also a USB device. And so we can, for this, I don't have one of the aluminum unibody machines, but this pre-unibody machine, I can change the keyboard firmware easily. Yeah, it's essentially the same concepts as I've presented so far. So we have this picture. A remote attacker can own the keyboard. So one thing is, whenever you're doing this, it's easy to brick a keyboard. So like say, suppose you make a mistake in the application checksum, then in order to fix that, you just reflash to the hex 69 firmware. So in order to do that, just change the argument from 220 to 228. And one thing is, if somebody is a malicious person, you can also intentionally brick keyboards. So what you can do is you can put like a well-placed jump in a particular location, and it completely bricks the keyboard. This is very easy to do. And the thing is, this cannot be fixed by reflashing. And you can choose the jump so that it's just completely hosed. And I don't plan to release the code for that, but in case anybody, since hardly anybody is interested in this talk anyway, if anybody wants to see a demo of this, there is an Apple store in Caesar's Palace. You can go buy a keyboard and I'll show you. I can completely brick that thing. The same thing for like the MacBooks and MacBook Pros. Oh, I don't want to damage any of Apple's products. So the thing is, this exact same thing you can also do to a laptop. If you own somebody's laptop, you can just completely brick the brick the keyboard on the laptop. Yeah. No. What you, I guess, I mean, this thing, like if you have, if that user is like an administrative user, and you're in that context, they're gone, they're done. You know what I mean? Most Mac users, they're running, whenever you're like install applications that ask you for this password, you don't need that password. And as long as you're in the context of that admin user, you can do this. So the reason why, and I have the slide, why does Apple need to fix this ASAP, is because suppose you have a bug in Safari, then what you can do is you can just craft you can create a specially crafted web page, and then have send a link to that web page to people who have Macs. They visit that web page, you exploit the browser, and you have remote code execution, and then boom, you can brick their keyboard easily. I mean, this is really easy to do, actually. And for a desktop, it's not as bad. You can plug in another non-Apple keyboard, but for laptops, it's quite bad. So this is a kind of a Chernobyl CIH, if you remember that piece of malware from a number of years ago. So, and in addition, you can also, of course, what I've demonstrated, you can install malicious code, like rootkit persistence and stuff. And you can also disable the firmware update mechanism and have permanent access. You can do it such that, change the code for the control endpoint such that Apple cannot subsequently issue a firmware update and fix it. You can completely have permanent access. The only way in which they can fix it is by taking the logic board out and then having another reprogramming it that way. Okay. So I want to thank Ben Fransdale. He's the guy who took most of the photos of the internals of the keyboard. I want to thank this guy, Script Blue from the Rochester Institute of Technology, Kang Lee at the UGA, Scott Moulton, who's sitting up here, and then Nathan Rittenhouse from MIT, who's sitting down there. Okay, so now I want to open up to questions. By the way, if you want to contact me, that's my email address. And I have a blog. I don't have a blog, and I don't really use Twitter, but in case I use them in the future, those are the addresses. Are there any questions about this? Yes. Oh yeah, it'll completely, say for example, what I can do is I can change it so that the keyboard can't even enumerate. You plug it in and it just won't, and it can't even enumerate. Yeah, I mean, I can make it so that it's constantly dropping on and off. I can do all kind. The keyboard is not usable. So if you want to, you can go to the Apple Store and buy one. I'll demonstrate.
So the flash process does depend on the firmware.
I'm sorry, say that again.
So the reflashing process does depend on the firmware.
Oh, yes, it does. Yeah.
Yeah, because what you said earlier, it sounded like it sort of wasn't. You said you could fix it.
Oh, that's whenever like the bootloader can still run. So suppose you send a firmware update image and then you mess up a checksum, then what happens is the keyboard is perpetually in a bootloader mode. And then what you can do is then you can just, you can't just use HID firmware updater with the original arguments. You have to change that product ID, then you can re-image it. But what I can do is such that I can brick it such that the bootloader can't even, the bootloader will first start up, and then what it does is it checks the validity of the firmware image, and then it jumps to this thing, but then I jump back to an appropriate location so that the whole thing is screwed up. And then the keyboard is completely bricked, and it doesn't, Apple can't have the opportunity to reflash it. So yeah, sorry for the confusion. Are there other questions? Oh, not many. Yeah, I mean this is not difficult or anything. This is not rocket science, but any other questions? I guess that's it. Okay, thanks.